Okay, so we're going to talk about a new set of problems this week. And there's 6 problems. The first 3 are probably more straightforward. Maybe the first 2 are straightforward. Third one is a little bit harder, but doesn't require too much knowledge, just a little bit more work. And then the last 3 probably need a little bit more thinking, especially the last one. So again, I'm assuming that you have read the problem, so I'm not going to go through the problem description, and I'm just going to get right to it. Okay, first problem is relocation. So you have a bunch of things on a line. You have a bunch of these companies on a line, and at the beginning, they tell you that there are N companies up to 100,000, and then you have a bunch of queries also up to 100,000. Each of these queries okay, the next N lines will be a number that is the location of the N companies initially. Each number is between 1 and 10 to the 9, so 1 billion, so a normal integer would be good enough. And then for each query, you have either 2 choices, either the company moved, or you have to figure out the distance between the 2 companies. Everything is between 1 and 1 billion, so everything can be done with just a normal standard integer. And basically that's it. So we have to come up with a way to easily figure out where everything is, because if we know where everything is, then we can just compute the difference between the 2 positions of the 2 companies, and then that's it. So we have to handle 2 different things. So the easiest thing to do, because there's basically only 100,000 things, would be use an integer array called position. Now, the IDs of the buildings or companies are from 1 to up to 100,000. So I have to make sure that I use 100,001, because if I just use 100,000, then the IDs are between 99,999. Or equivalently, I can just make sure that whenever somebody gives me an ID, I subtract 1 to make it go to 0 to 99,999. Either way, it's fine. And then, of course, at the beginning, all I have to do is read it into this array. And if there's a change, so if it says 1 and then company followed by the new location, then all you have to do is say position of the company C, it's now at X. Okay. If they tell me, give me 2 companies and what is the distance between the 2, all I have to do is compute position A minus position B and take the absolute value. And in C++, you can take the absolute value just by this. And notice that for each query, each one can be done in constant time. I don't know. I'm just looking at an array. If you don't like array, you can use vectors, but in any case, both updating the location and compute the distance between 2 companies are both constant time. So that's pretty much all you have to do. And so I'll just very quickly show you my code. So here we are, right? So I decided to use 100,001, and then I have to be careful that my loop goes from 1 to n instead of 0 to n minus 1. And then for each query, either it's command type 1 or command type 2, and that's all there is to it. Okay, so there's not much more to say. I'll move on to the next problem. Okay, character developments. You have a bunch of people n up to 30 people. This can be 0. How many relationships do you need to explore? And it says that the relationships that need to be explored if there's three people, for example, then there are four relationships. The one between each pair and the relationship when all three are together. In general, the relationship between all subsets of at least two characters must be explored. Okay, so all subsets of size 3 or more. So size 2 or more. Okay, so how many subsets are there of size 2? And choose 2. How many subsets of size 3? And choose 3. How many subsets of size 4? And choose 4, and so on. And that's one way of computing the answer. So you get a binomial coefficients of n choose k, where k goes from 2 to n. If you know how to compute binomial coefficients, and that's the end of that. But equivalently, you can also say the number of possible subsets of n things, which is this, it's 2 to the n. Okay, so you should know this. The number of ways you can choose a subset of size n, the subset out of n objects is 2 to the n, because for each element, either you include it or you don't. What you want is this chunk. So what you can do is you can just say this chunk is 2 to the n minus n choose 0 minus n choose 1. This would be the easiest. So, I mean, you can do the sum if you want, or you can do it the other way. And why is this easier? Because this is just 1, and n choose 1 is just n. So altogether, the expression is just 2 to the n minus 1, which is relatively straightforward to compute. How do you compute 2 to the n? I suppose you can take 2 and multiply it to by itself n times, or you can do this. So in C++, this is a left bit shift. So this says take 1 and shift it to the left n times, and what that means is it adds n zeros. And in binary, that's basically 2 to the n. So this is an easy way of doing this. And finally, if n is at most 30, that means this is at most 2 to the 30, and that also fits inside a standard integer. So you don't have to worry about using 64-bit integers. So code, it's fairly straightforward. And that's it. It's just a one-liner after you read in the input. Okay, so that's character development. Okay, the next one is a little bit more involved. You have basically these log entries. Every day starts with an open, goes until close. And for each day, you have a bunch of people entering and leaving at a certain time. And for each person, you have to figure out how long they have been at the park, and then charge them 10 cents a minute or something like that. Yeah, 10 cents for every minute. So this is a bookkeeping exercise, basically. You have to also print things alphabetically by customer name. So the standard thing to do, I guess, would be to have a map where the key is the name of the person and the value is whatever we want to keep track of. So in this case, we need to keep track of two things. We need to keep track of when a person has entered the park. So when we know that they exit, we can figure out how long they've been here. And then we also need a map that stores how much money each person has spent. Now, one thing that you have to be careful, if you read this problem carefully, it just says that, where does it say? Each enter has a matching exit sometime later today, and no enter reports for a customer who's already in the park, and no exit reports for a customer who was not previous in the park. At the start and end of each day, the park is empty of customers. One thing that they did not say is that a person can enter, leave, and enter again. And because they did not rule that out, you have to take that into account in your program. Now they're actually nice to you because in the sample inputs, if you forget about this, they actually have a case where Sam enters and exits and then enters again. So if you forgot to, if you didn't realize that and you write your code assuming that each person can only enter and exit once a day, then you would be caught by this sample input, but they didn't have to be that nice to you. And then you'd be scratching your head trying to figure out why your program doesn't work. All right, so what is our plan? Our plan is to keep track of, for each day, okay, we're going to keep track of a map that goes from the person name to the time that that person enters, and also another map that maps a person to how much money they spent that day. Okay, every day we can reset this because every day is treated separately. We don't have to give a running total of the days. So we'll just treat each day separately. Now, when somebody enters, what do you do? So that is, we call it map 1 and map 2. You insert entry to map 1. Okay. When somebody exits, what do? You look up entry to map 1. Look up entry in map 1, sorry. Let me just in map 1, and then add costs for that person to map 2. Now, it's important to say add and instead of just assign, because somebody could have entered and left the park and enter again, so they might have already have a running total. So we have to remember to add the cost. Also, it's important to remove entry in map 1. Okay, because the person has left. Now, I suppose you can say maybe it's okay to not remove it because if enter, instead of just inserting, just update the entry. If there's already an entry that's there, then that's good enough. Okay, so this is optional, provided that you process the entries properly. What other things do I want to talk about? The other thing that I want to talk about is the cost. It's the number of minutes times 10 cents per minute. And you're supposed to print your answer in something like, $6.50 or something like that. Now, how are we going to store the cost? You might think that since this is a floating point number, we're going to sort it as double. And that is a really bad idea because doubles generally can have it's a floating point number that can be rounding errors. And in general, when you deal with numbers, with dollars and cents, it is actually better to store the cost in cents, and you store things as some kind of integers. In this case, a single integer would be good enough. A 32-bit integer would be good enough because the total number of minutes in a day is not that much, 24 times 60, and then 10 more cents. It's definitely way less than 2 to the billion. So it's better to store it as an integer in cents, because that way you have no rounding error. And then when you print it out, the dollar would be the cost divided by 100. And this would be the cost remainder 100, but you have to be careful, maybe not in this case, but in other case, it's 6.05. When you print it, it might just print a 5 if you don't, if you only have one digit in this sense. But we'll explain how to deal with that later. Okay, so that's basically it. And I'll show you the code. So the wrong answer actually is just basically me removing the update of the cost in the case that somebody enters after they exit multiple times. So I just want to confirm that there's at least one case that fails. Okay, anyway, I'll just show you my code. So my main loop looks a little bit weird, but the idea is that basically I want to call a function that processes one day at a time. And this function will return true if it was successful and false otherwise, because things are done through NFL. So maybe I try to process the next day and there's no more days. And then outside in the main program, I keep track of a counter that says how many days I have done so far, so that I can print the correct number of days. Okay. And then the way that I strongly advise people to do this instead of trying to put everything in main, because you have another level of nesting, and then you have to make sure that things from one day is not saved to another day, and so on and so forth. Okay, so the process function, first I read a string, and this here is a shorthand to say I try to read the string, and that returns it returns a value that can be valid as true or false. And if it's false, that means that the last reading operation was unsuccessful. So how can it be unsuccessful? Because there's no string to read, because it's NFL. So if you try to read the first thing during the day, if it was unsuccessful, that means there's nothing more. So I return false. Otherwise, at the end, I have some process something, so I return true. And the first thing in a day must be open. So I use an assert to just check. And the reason why I use assert is that if for some reason the first line in the day is not open, my program will crash. I'll get a runtime error. And why is that a good thing? Because if I don't do that, and then if I really screwed up my inputs, I might just get a wrong answer and I wouldn't know why. But if I get a runtime error, it means my program crashed, and I will look everywhere to see where my program can crash. And this is one place where I specifically say, if something I expect is not true, crash. And that will help me potentially isolate the problem quicker. Okay, so then I have two maps. One that I call enter, that's the time that they enter, and then total, that's my cost. I have a loop that keeps reading the next command, and as long as the command is not closed, I do something. So what do? I read in the name and the time. If it's the enter, then I just insert this. Otherwise, if the person left, so I compute the elapsed time, that's the current time minus the entrance time, times 10 cents per minute. Now, this actually is not absolutely required, because when I enter, even if there was an entry there, I would have updated it already. So it's not absolutely required that I erase the old time, but I thought I'd keep the map more clean. In fact, I can just quickly show you that if I get rid of this line, it will still be accepted. Okay, and then I got to print out everything. So one thing that they say is that let me go back to the problem statement. It says output leave a blank line between reports for consecutive days. So after day one, but before day two, there should be a blank line. After day two, before day three, which should be a blank line. There should not be a blank line after every case. So there should not be a blank line after the last day. And there should not be a blank line before the first day. So what I do is that I print a blank line at the beginning of the day, as long as it's not day one. Okay. If it's day two, day three, day four, and so on, I always print a line to start. Then I print the day, and then it says print all the cost alphabetically by name. So I go through the map are already sorted by name in alphabetical order, and this is a quick way to grab things from a map because each entry is a pair. So I just assign, so this notation, auto square bracket, and then something comma something will assign the first entry of each pair in its name, and the second entry is cost. So this is a key and value pair in a map. I print out the name, I print out the dollar sign, I print out the dollar, which is the cost divided by 100 because I'm keeping the cents. Print the dot, and here I'm printing the cents, but I want to make sure that even if the cents, let's say a penny, it will not just print one, it will print 0, 1. And the way I do it is to say that I want to print it with 2. So you always use a space of 2. And if there are any blank spots, fill it with 0. Now in this case, because everything is 10 cents per minute, this will never happen. So I actually don't need this, but I want to show you how you can do this in general. Okay. Okay, so that's not amused. Okay, the next problem is called Colors War. So basically, they say that they asked a bunch of people, up to 10,000 people, and each person will say that in their group, in that person's group, there are, 30 other people or whatever number of other people. And you're trying to figure out what is the minimum number of people that can lead to these observations. Okay, so they may not ask everybody in the group, in the whole school, but of the people that they ask, they will tell you how many, for each person, how many other people it's in the same group, that person. Okay, so again, I'm not reading the problem statement with you. I'm assuming that you have read the problem statement. All right, so let's say that the answers are like 5, 7, 4. Okay, so right away, if you have only asked 3 people, and person 1 says that they're in a group of 5 other people, that means that this person 1 cannot be in the same group as person 2 and person 3 because they are all in different group sizes. So person 1 must be in group of size 6 because person 1 is in a group with 5 others, so the size is 6. Person 2 must be in a group of size 8, and person 3 must be in a group of size 5. So altogether, it's 19. That's the minimum. Okay. There might be other people in groups that are not related to person 1, 2, and 3, but we can't take care of account because otherwise there's no unique answer. Okay. So if all the numbers are different, they cannot possibly be in the same group. So you treat them separately. So similarly, even if you have another 2 people, maybe one of them has 5 and one of them has 5, then the 7 and 4 are treated independently because they have nothing to do with the people with 5. Okay. But these people with 5s, they can potentially all be in the same group because each person says they're in a group with 5 others, so they can all be in this group. So just having more fives doesn't really change anything. The answer is still 19. What if I have more five? Right, where have I more five? I have another person in a group of five, and a person in a group of five. I can have 6 people in a group of five, in a group of 1 and 5 others, and the answer doesn't change. But if I have one more person that has 5, then it's not possible for them to be all in the same group because there's 7 people here, and the same group can only take 6. So now this person has to be in another group of 6, and so you need to add one more. So let's, first of all, what are the 2 observations? Different sizes. We solve independently. Don't have to worry about the different sizes mixing together, and then add them up. Add up all the answers. And then we look at all the things of the same size. So of a certain size, S. So remember that size S is actually whatever they tell me plus 1. Okay? Because if they say 5, the size is actually 6. If the size 6 has, I don't know, let's call it M responses. So for example, if size is 6 and then there are, I don't know, 13 responses, then how many groups are there? The number of groups must be M divided by S rounded up. Right, so in this case, 13 divided by 6 is 2 and a little bit. And then when you round up, there's 3 groups. Because 2 groups is not enough, 3 groups is enough. On the other hand, if you have exactly 12, then dividing 12 by 6 is 2. So 2 groups is enough. Okay, so to deal with a specific size, whatever that size is, you look up how many responses there are of that size. Do this calculation, that's the number of groups. And of course, the number of people is just the number of groups divided by, multiplied by the size, which is this. Okay, so that's kind of all you have to do. There are a couple of questions. How do we keep track of for each size how many responses there are? Well, we can use a map that basically maps the size to the frequency. Okay, so that's whatever name you want to call the map, that's fine. The other question is, how do you compute ceiling of M divided by S? Now, these are all integers, S and M. So M slash S, if you just do that as integers, that will give you the floor of M divided by S. So let me not write it this way. That will give you M divided by S rounded down. Okay, actually, I need to make a little bit of disclaimer. Whatever I write here, disclaimer, this is only true if M and S are at least not negative. If M and S are negative, this may not be true. Okay, but for non-negative M and S, M divided by S like this is M divided by S rounded down. Now, there is no easy way to round things up, and so some people might say, okay, well, let's do a static test of these things. One of them divide by S, and then you call something, there's a function called ceiling, which round things up. And this should be avoided at all costs because you're taking integers, you're turning your floating point numbers, divide by S, that can introduce rounding errors. and then things can be incorrect because of the rounding errors. So we don't like any of that. We want to close it out. Do not do this. So can we do something? Can we divide and round up using only the integer operations? And the answer is yes. It turns out that if you do m, you're trying to divide by m by s, and you want to round it up, what you do is before you divide, you add s minus 1, whatever you're dividing by minus 1. Okay, that's will end up giving you rounding up. Again, it's assuming that everything is not negative. Okay, so why does this work? If you're dividing, so this mathematically, the way I write it, is something like this. Okay, if when you divide here, m has a remainder that is not 0, any remainder, when combined with s minus 1 here, will push this to at least s over s minus s over s, right? So if this is a little remainder, even if it's just 1, this will push this over to s over s, which will then push it over up by 1. If it's more, if you have bigger remainder, you'll push it up by, it will still push it up to 1, something bigger than s divided by s, but it can never push it up to more than 2s because the biggest remainder you can get here is s minus 1. So the biggest thing you can get over here is 2s minus 2, which is when you divide with the standard integer division and round it down, this would just be less than 2. So it will just be down to 1. So this trick is used to divide and round up integers using only integer operation. Okay, so with all of that, I'll just show you my code. So again, my code is relatively short. So we're reading n, I read in this frequency, that you have this frequency table, and this time I just, for each thing that you give me, I just increment it. So I know frequency for each input, how many times I see that input. I have my answer, which is initialized to 0. And then just go through all of the entries. Again, V is the input, and F is the number of times. So the group size, which I call S in my slides, in my whiteboard, it's just V plus 1. And then this basically is F divided by group size rounded up, the frequency number of times, and then the number of people is just the number of groups times the group size. All right, so coding itself is not too hard for this problem, I guess, but you need to know how to code, right? There are a lot of little things that goes on. You have to think about what's going on first. Then you have to know how to do, most importantly, how to do this sealing when you divide. Okay, so now there's this Deathstar problem. I'm not really sure what this problem has anything to do with Deathstar. Again, I'll just go straight to the discussion, assuming that you've read the problem. So you have an array, you have a square matrix, and you're given, oh, sorry, not given, you're told that you started with A1, A2, A3, up to AN, which are some numbers. And each entry in the matrix, Aij, it's equals to the bitwise AND of these inputs, the numbers that you're trying to figure out, AI and AJ, bitwise. Yeah. Okay. And then you're trying to figure out a possible set of starting values of A1 up to AN that will give you this input matrix. You are also told that the diagonals are zeros. Why? Because if the diagonals are not zero, then these diagonals are just AI and AI, and then you just basically it's AI, so you just read off the diagonals and you're done. You don't have to do anything else. So the diagonals are zeroed out, so you can't get any information. Okay, so bitwise AND means that we have to look at the binary representation of these things. Now, when you see something here, whatever this, let's say AIJ, if AIJ in binary is, I don't know, just make up some binary, and then just like this, so capital A, the matrix. Then what do you know about AI and AJ? Well, this remember is a bitwise AND of AI and J. So if it's zero, then I know nothing because the only thing I know is that they cannot both be ones. They can be both be zero. One of them can be one, the other one can be zero. I don't know anything too much more. But when I see a one, I know for sure that both of them are ones in those locations. And basically that's all I'm doing. Okay. So maybe later on I see that the next location, AI J plus one, would have another bit pattern. And then based on those bit pattern, I would go and turn on the corresponding ones of AI. And that's pretty much it. Okay. So it turns out that it's actually kind of easy. So basically, I look at AIJ and I go and turn on the corresponding one bits for little AI and little AJ. How do I turn that on? All I have to do is say AI is equals to AI bitwise OR of AIJ. How do I do bitwise OR? It's a single vertical bar. In fact, I can even just look at this and I say AI vertical bar equals AIJ like this. These are the bits that must be turned on. Okay, can I turn on more bits? Maybe, but I don't have to. Okay, they must be turned on. I have no choice. If I don't turn them on, it will never work. Okay, so does it guarantee that it works? If I turn them all on, the answer is yes. Okay, it cannot not work, I guess. You might have to think of it a little bit about why that is the case, but I'll just leave it at that. So the code, again, this is more of a thinking problem, but the code itself, it's fairly short. I have an array of A's, and then I just for each entry from I and J from 0 to N, I read in the entry. If I and J are the same, I skip it. Otherwise, I just do a bitwise OR to turn on AI and AJ, and then at the end, just print it out. Okay. Okay, the last one is probably the hardest one. It's meant to, it's a bit more of a challenge for the more experienced people. Probably people that have done 3620 at least, but even that, maybe you don't know. Okay, so you have up to 1,000 people and the 5,000 pairs of people that can see each other. You want to say who can shoot who, but every person can only shoot one person, and you want to make sure that everybody's shot. Okay, so what are the features here? You have N people, M pairs, and whenever you see this, you probably should think about a graph of some kind. Okay, so you have relationship between people and you have N people and so on and so forth. And some people can shoot each other, but not all. So you probably should think about a graph to model the relationship. Now, every person has one bullet, can shoot one other. I suppose they can shoot themselves. Um, it was explicitly said that, but I don't think you want to do that. Every person can shoot one other. So let me just check. Can you shoot? Oh yeah, okay, so it says that actually the pair that can shoot each other, it had blah, blah, blah. Okay, if a pair, if a player can see another player, he can fire at him, and then the only ones that he can see, they will give you the pair A and B, and A and B. A is less than B, so they will never give you A can see themselves. Okay, so you never shoot yourself. Okay, shoot one other, and you want to make sure that every person is shot. Now, whenever you hear these constraints where every single thing, every single person can do one other, can go to one other thing, and every person has to be done by somebody, it's usually what is called a matching problem in graph. Okay. And there are different types of matching. The best, the easiest kind of matching is what is called bipartite matching. What is bipartite matching? Bipartite matching says that you have a graph with a bunch of nodes on two sides, left and right. They don't even have to have the same number. And you have some edges, and these edges can only go across from left to right. Can never go. Okay. And you want to choose some subset of edges. So maybe this one, and this one, and maybe this one, and this one, and maybe this one. You want to choose some subset of edges so that every edge, oh wait, that doesn't work. So that every edge touches, no, sorry, every vertex is touched by at most one edge. So if I chose this edge, then this vertex would have two. So that wouldn't work. And and what you want, it's a maximum bipartite matching, which is to find the largest number of edges so that no edges will touch a vertex twice. So in this case, I chose 4 edges. It is not the maximum because I could have not choose this, but instead choose this one, and now I have chosen 5 edges. In this case, it's a maximum because everybody on the left has matched. Not everybody on the right has matched, but it's impossible because there are more things on the right than left. So this is pretty much the best you can do. All right. So now the question is, are we okay? Okay, so then there's a general matching problem, which is not a bipartite graph, but a general graph. And it maybe you have edges like this, I don't know. And then you want to choose, I don't know, this edge and maybe this edge, and that's all you can do. Okay. But maybe other problems, like if you have another edge here, then all of a sudden you can decide to choose maybe I choose these 3 edges. And now you basically pair everybody up and no edge would touch more than one, no vertex would touch more than one edge and so on. So general matching, when you don't have uh, your nodes separated into left and right, it's actually much harder. Okay. So I'm just going to say this is hard. Now, it's hard for us, I guess, especially for people that are just starting out. But if you're talking about people that go to the World Finals, this is not something that they consider hard. But anyway, for us, we will just not worry about this. Bipartite matching, if you've never seen this before, I guess it's still going to be hard. Um, you can look up algorithms and so on, but I'll just say that in the code library, so if you go to my repository, GitHub repository code library, you can go to source and something called matching. Now, this is actually written a long time ago. It's even in C. You can use it in C++. And you have to figure out how to use it. We have a more advanced version, a more updated version that's actually not in C, but that's in this particular subdirectory ICPC, which is version that we take to more advanced contests when we advance to the World Finals and so on. And it uses some other things. So it uses something called graph layouts and so on. Anyhow, the point is, so there's graph layout. Graph layout tells you how to have a graph data structure. But anyway, the point is not so much, you know, the algorithm itself. At least I don't want to talk about how this algorithm works. If you want, you can look up this thing called alternating path, and that gives you an idea of how you can implement it. Although the algorithm that's in these libraries are actually faster than that. Anyway, if you can model your problem as a bipartite matching, then you just call the functions and you're done. But there's a problem. The problem is bipartite matching requires two sets of nodes, one on the left and one on the right, and nobody in between. Nobody that says that everything goes, all the edges goes between a left node and a right node. So how do we decide, the people, which one is left and which one is right? Right? For a person, is it left? Is it right? How do we decide? And here's a little, I guess here's the insight. If I have n people, I'm going to actually make each person as two nodes, because each person has two roles. One is to shoot somebody, and the other one is to be shot at. So for example, if there's a line of sight between A and B, that means A can shoot at B, but also B can shoot at A. So I'm going to look up A and B, and I'm going to say that A can shoot at B, and B can shoot at A. I'm going to build a graph this way. And maybe somebody else, maybe A can also shoot at C. So it's C, A can shoot at C, and C can shoot at A, and so on. And once I set up this graph, now I am basically looking for a set of edges that go across so that each edge touch each node on either side once. And if I can find exactly n edges, the maximum matching is exactly n edges, then I'm good. I'm done. So if you understand what I just said, then all you have to do is set up your graph and call the function. So the first part is just, including the library. Okay. So in real contest, you have to write it up, but then just assume you copy and paste. But of course, you also have to know exactly how this is done, how to use it. So there's something called bipartite graph, and max U and max V has to be defined so that the max U and max V are the maximum number of nodes on each side. And then here, I just I read in A and B, and because I think the IDs are between 1 and 1000, I want to make it between 0 and 999. So I just make them A minus 1, B minus 1, and I just set things to be true if there's an edge that goes from A on left to B on the right and vice versa. Because this is a global array, it's automatically initialized to zeros, and zeros means false. Then I call this function match, which takes two parameters, number of things on the left and number of things on the right. In this case, both are and then it's going to return, well, it doesn't return anything. It's all global variables. It's going to tell me that on the left, so matching of 0 is equals to 5 means on the left, 0, it's matched to the thing on the right at number 5. So 0 shoots 5. But if there's no matching in the maximum matching, it remains -1. So basically, I want to know if there's anybody that has the -1 matching, meaning that somebody doesn't know where to shoot. So I just say, let's look in the matching array and find -1. So I'm using the stl find function. If I can find -1, then it's impossible. Otherwise, I just print out who they're supposed to be shooting at, remembering that my IDs are from 0 to 999, so I have to add 1 back to get 1000. Okay, so this is a classic problem where if you know how to model things and you recognize one of the classic problems, and you recognize that you have the algorithm in your library, whether you have done it yourself before, you know that we have this library code, all you have to do is pull out the hammer and hit this nail, right? So many of the problems, the more, I guess, medium hard kind of level of problems, especially with graphs and so on, it's about recognizing how you model the problem to make it look like something, a well-known problem, in this case, matching. Now, even if you've taken 3620, you might not have seen the matching problem. Probably you haven't, but this is a good time to learn about it. Okay, so that wraps up this week's problem set, and I'll stop here.